Okay, so we're supposing R is an equivalence relation on A, S is an equivalence relation on B, and A and B are disjoint. And we've already shown that, okay, so we have R, an equivalence relation here, S here. We've already shown that if we take the union of, a little bit of trouble here, the union of those two equivalence relations, then that will be an equivalence relation on the union of the two sets. Okay? So in part B here, we're supposed to prove that for all x in A, so take some element x in here, its equivalence class with respect to the relation R union S equals its equivalence class with respect to the relation R. Okay. So what does that mean? It means that basically the set of everything that is equivalent to in this relation equals the set of everything it's equivalent to in that relation. Okay. So suppose this is the equivalence class in the original R relation on A. Okay, so it's x is equivalent to everything else in this little piece of A. Well, in the R union S relation, we also want to ask, is there anything that x is equivalent to via S? And the answer is no, right? The relation S lives completely over here. All the arrows are among things in B. So x is not equivalent to anything with respect to the relation S. And so adding that in doesn't make the equivalence class any larger, right? Or of course any smaller either. So that is why we expect those to be equal, and exactly the same reasoning would hold for an element y over here and its equivalence class with respect to S. Okay, so let's try to write down a proof of that. We have our equivalence relations, and then we're going to use what we proved in part A, that R union S is equivalence relation on A union B. And here's our goal. I only need to prove the x one, right? The y one would be exactly the same proof, but with replacing x's by y's and a's by b's and r's by s's. All right, so we let x be an arbitrary element of A, and we're going to prove that, and we'll also let z be arbitrary. I kind of dropped that quantifier, right, already. And then we're going to prove that z is an element of the left-hand side if and only if it's in the right-hand side. Okay, so let's do the two directions, and we'll take the forwards direction first. And we'll do direct proof, so we'll bring z in x bracket R union S over as a given. And by the way, I've brought down, since A and B are disjoint, I have A intersect B as the empty set, which gives me that one way to write that is that for all x, if x is in A, then it can't be in B, right? Now the reason I'm writing it that way is because I have x in A up here, and so if I do a universal instantiation, okay, come back to that in a minute. Okay, so what does that mean? I'm trying to prove that z is related to x by the relation R. Okay. All right, here's my universal instantiation, and together with x in A, that gives me that x is not in B. And okay, z being in that equivalence class means that z is related to x, right? Zx is in R union S, and Zx being in R union S means that either Zx is in R or Zx is in S. Now, I would love to rule out the possibility that Zx is in S, because that would leave me with my goal, right? So why can't that happen? Well, remember when I was drawing the picture, the issue was that x can't be in B, it's because it's in A, right? And these are disjoint sets. And in particular, then Zx is not in B times B. The second coordinate x is not in the second set B. And, well, since S is a relation on B, right, in other words, S is a subset of B times B, well, if you're not in the bigger, bigger set, then you're certainly not in the smaller set. Okay, so there's some, I think that's a modus tollens going on there if you work out the definition of what it means for S to be a relation on B. Okay, so that means that it's not true that z is related to x via S, and if you combine that with our disjunction up there, then a disjunctive syllogism gives you our goal of zrx. Okay. Good. Now you may decide you don't like this notation where we put the relation name in between the two elements, and that's fine. You can just stick to the ordered pair notation if you prefer that. All right, so in our proof here, we are letting x be an arbitrary element of A and letting z be arbitrary, of course. We're going to show this if and only if that. So what we just did is this forward direction here. Okay, we proved that z is in x bracket R. All right, now for the backwards direction. It's going to be, I think, a little easier. Okay, so this time we can get rid of the equivalence class notation, and then we can put that in ordered pair notation. And that does it, right? Because if zx is in R, then yeah, then zx is also in R union S. So that's the easy direction. See it right there. And then, like I said, we're supposed to do this for y and b too, but that proof's analogous, so I'm not going to write that one down. And you wouldn't have to either if this were a homework problem. You can just say it's the same thing. Okay. All right, well, there is also a part C to this problem. So here it is, well, same setup as before, and we're supposed to prove that, goodness, the set of R union S equivalence classes is the union of the set of R equivalence classes with the set of S equivalence classes. Okay, so I mean, this kind of makes sense because remember we had, I won't draw the rectangles again, but we had the R equivalence classes over on the left in A and the S equivalence classes over on the right in B. And well, we said that when we move to this new relation, those classes don't change at all. So all the classes would still be the things you had before, just the union of the stuff on the left and the stuff on the right. Okay. So how does this work out proof-wise? Well, we're showing these sets are equal. So and these are sets of equivalence classes, right? So I should use a capital letter here because an element of this is going to be it's going to be equivalence class, and therefore it's going to be a set. So let capital Z be arbitrary. We got to show that Z is on the left side if and only if it's on the right side. So we have the two directions again. Let's do forward direction first. And over here I've just written down what we just proved in part B because we're going to need that. Okay, so we do direct proof, bring over another given. And the fact that Z is in this set of equivalence classes means that Z is an equivalence class, right, with respect to this relation R union S. So that means we can find some element little z in that set such that, oh, that's too bad. This would be a capital Z right there. I wonder if that carried through. Such that capital Z equals this equivalence class. Okay. Right. And then, okay, well, this is just proving that Z is in the union, is showing that it's in one or the other. Okay, so then we get a disjunction out of that. Okay, well, that typo there, it looks like it was a one-time occurrence. Sorry about that. It should be capital Z. So we just want to do existential instantiation. So we get that there's some Z naught in A union B such that X equals the equivalence class of Z naught. And, okay, but we want to show that Z is the equivalence class with respect to just the relation R or just the relation S. Okay. And, well, we got a disjunction, so we got to do two cases, right, over in the set A or over in the set B. If we are in either one of those, then we know that by part B, right, by these universal statements up here, okay, if we have Z naught in A, then we can do an instantiation here where X is Z naught. So we get the Z naught bracket R union S equals Z naught bracket R. And similarly, since Z naught's in B, we can do universal instantiation here with Y equals Z naught to get that Z naught bracket R union S equals Z naught bracket S. Okay. So the fact that, right, and then we can say that, you know, we can replace Z naught bracket R union S by capital Z, because that's what capital Z was. So basically, we went from having capital Z being an R union S equivalence class to, in one case, being an R equivalence class, or in the other case, being an S equivalence class. Basically using what we did in part B. That's where all the hard work was. So now we're basically done, because we can decide that in case one, we're going to prove that capital Z is an R equivalence class. And in case two, we've proved that capital Z is an S equivalence class. So that takes care of it. So you can take a look at what that would look like in a proof here. You see then by part B shows up in both cases. And now let's spin around in the other direction. So this time I'm assuming that Z is either an R equivalence class or an S one, and I have to show that therefore it's an R union S equivalence class. So we get our disjunction, and surprise, surprise, more cases. And in the first case, if Z is an R equivalence class, then by definition, there exists an element of the set A such that Z equals that equivalence class, right? And existential instantiation gets us to an X naught. And we have the same goal in both cases this time. Okay. Here's where we pull in our our results up here from part B. In this case, the first one, we'll do instantiation where X is X naught. And so we get that X naught bracket R union S equals X naught bracket R. And that tells us something about capital Z, right? And can replace this over here by capital Z, and we get that, and that's exactly what we need. Because, okay, well, we had to say that X naught is not only an A, it's an A union B too, right? And so because it's an A union B, and because Z is its equivalence class of X naught, we have that Z is in that set of equivalence classes. Okay. And you can imagine doing precisely the same thing when Z is an S equivalence class, but you're going to use this second universal statement up here instead, and that'll give you the same result. Okay, so you can also take a look at that one over here, the backwards direction. We suppose that Z was in here, and I didn't write that there, did I? And then we end up showing that, well, you see it here, that Z is in the set of R union S equivalence classes. All right, that's it.